Okay, so chapter 13 deals with calculus and vector fields. And one important application will be to determine, like if you have a particle in a vector field in space, and the field, has forces acting on the particle, moving it from one point to another in space. We want to know what work the force field does in moving the particle from one point to another in space. That's an important concept. So, uh, the field could be a velocity field like wind, could be, a lot of things. So let's get our heads wrapped around on what a vector field is. So here you have examples of velocity vector fields. Okay, so in San Francisco Bay, wind patterns. So winds have direction. They have direction in speed, right? They have well, we could model wind by vectors, and the direction of the wind is given by the vectors, and and the velocity of the wind can be given by the lengths of the vectors. Okay, so in this figure here, in this figure figure 1, it shows velocity vector fields in showing San Francisco Bay wind patterns. And you can see the patterns vary and all that. What are some other examples of vector fields? Well, here, okay, you have in figure 2, so we saw figure 1, and now we're in figure 2, more vector fields, velocity vector fields. So ocean currents can be modeled with vectors, and airflow in part B there in figure 2, the second picture, you have airflow past an inclined airfoil. So, vector fields, very important. So, you can have 2-dimensional and 3-dimensional vector fields. And a vector field here, a vector field in a plane is a function, a vector function f, that assigns to each point a 2-dimensional vector. Okay, so let's get concrete here. Let's look at an example. So, okay, well, so you have here a vector field f that's a function of x and y, and the components of the vector field, the I and j components, are also functions of x and y. And we can abbreviate this in short using this notation. Okay, so when a vector field f is equal to p times I plus q times j, it's understood that p and q are functions of x and y. So how do we draw a vector field? Okay, I mean, here's a vector field. How do we, let's look at one where we can draw one. This is a 2-dimensional vector field, by the way, in figure 3. And figure 4 has a 3-dimensional vector field. We're living in a 3-dimensional vector field, right? What 3-dimensional vector field are we living in that all of us on Earth are living in? Can you tell me? What's always acting on us? Gravity. That's right, Robin. A gravitational vector field. Yes, Eric, electromagnetic, and I don't want to get too technical here, but yes. So I always think of the gravitational field. And, if we wanted to draw a 2-dimensional vector field, like for instance here in this example 1, a vector field is defined by negative yi plus xj. So they want us to draw the vector field, draw this vector field by sketching some vectors. So all you really need to do is pick some points. Okay, and draw the vectors. So like for instance, at 1, 0, at the point 1, 0, well, the vector field is negative yi plus x times j. So, the actual then vector at the point 1, 0 is the vector 0, 1. And you can see in the figure they're drawing a vector 0, 1 at the point 1, 0. Okay, and then like for instance at 2, 2, the vector is negative 2, 2. So in this figure 5, at the point 2, 2, they draw the vector corresponding to negative 2, 2. And you can plot many vectors, and then you at every you can pick many points in the xy plane, and at each point draw a vector. And they do that. They draw a lot of vectors in this. They draw a lot of vectors. And then they plot all the vectors in the field in figure 5. They plot all the vectors there, and that gives you your vector field. Now, fortunately, we have MATLAB that can help us graph vector fields, and we'll talk about that in our next class. But basically, we want to use technology to help us draw vector fields, but a lot of times you can tell just by sort of looking at the, just using your instincts. Given a formula for a vector field, you can picture what the vector field looks like. And that's like in figure 6, the negative y x vector field. Okay, so every quadrant in the xy plane, x and y is either positive or negative, and based on that, this is what that field would look like. Okay, you can have a field, for instance, figure 7, where you have the first component is the y component, and the second component is the sine of x. Okay, so you have a lot of really interesting looking vector fields. We could take this to 3 dimensions, 3-dimensional vector field. Okay, so if you have the vector field given by z times the k vector, well, that is what the vector field looks like. Now notice as we move away from the xy plane, either up or down, the vectors are growing larger in magnitude. Why would that be in figure 9? Well, also the vectors are vertical vectors because the I and j components are 0. And definitely as you move away from the xy plane, that's right, Ryan, z increases as you move away from the xy plane in the vertical direction. So the vectors should increase as well. Okay, does figure 9 make sense? Does that make sense to you? Robin's good with it. Are there any questions on figure 9? All right, well, let's keep moving then. Let's keep moving on. So, okay, here are other 3-dimensional vector fields, a little more interesting. Okay, this would be the vector field with components y, z, and x. Let me show you the second one. Look at this vector field in figure 11. what do all the vectors seem to be doing? This always reminds me of those, ever see the movie The Mummy? The Mummy with all the bugs? That's what this kind of activity reminds me. Well, you know, they're definitely going one way. What way are they going? Are they going left or right, these vectors in figure 11? I mean, are the vectors going left or right? And all right, do you adopt? That's right. And why are they going all left? What's causing all these vectors to go left? Something in the formula must be making the vectors go left. The negative j, that's right, Jamal. And in fact, the negative 2 in front of j is constant. So no matter where the vector is, no matter what coordinate, x, y, z coordinate the vector's drawn at, the j component's always negative. So the vectors have to be going left. They can go up, they can go down, depending on where you are in space, depending on where the vector starts from in space, what point it starts from, but it's always going to be going to the left. Okay, are there any questions on that? Okay, well let's move on here. So, you know, you can have velocity fields, okay, in physics. How many have seen velocity fields in fluid flow in physics? How many have seen that kind of thing? Maybe. Of course, we're going to be getting into some fluid flow type situations later on in chapter 13. Something called flux. I don't know if you've heard of flux, but we're going to be getting into that. Okay, all right. Let's continue on here. Gravitational field. How many maybe have seen this formula in a physics class for gravitational field? Between two objects with masses. Okay, Ryan's seen it, John's seen it. G is a gravitational constant, and R is the, hold on here, distance between the objects. Okay. So of course, if the distance between the objects increases, as R increases, what's going to happen? What's going to happen to the magnitude of the gravitational force? As two distances get further and further away from each other, what happens to the gravitational force between the objects? It approaches zero. It gets less and less. Absolutely, absolutely. Okay, all right. So you know, now if we were to write out the gravitational field in terms of its components, this is what would be what the components are. And we have a picture here. We have a picture below that shows an example of a gravitational field, gravitational force field. So the origin would be like the center of the Earth, and there's your gravitational force field. Are there any questions on that? Okay, well, let's continue then. Let's continue. Okay, electric force fields. Okay, suppose an electric charge is located at the origin. According to Coulomb's law, hold on, I want this to show a little better, yeah. According to Coulomb's law, the electric force exerted by the charge on a charge q located at a point xyz with position vector x is given by that formula. Okay. How many maybe have seen that in a class? Okay, Marvelous has seen it. Okay, all right. So, I'm trying to relate this to classes you've had, or maybe are going to have, right? Let's continue. Let's continue. So, all right, electric fields, very good. Let's continue here. Gradient fields. All right, so the gradient function can be written, well, you know how gradient's defined. You know how gradient's defined. Okay, and hold on here now. I want this to show properly. Yeah, so a gradient field is given here. And really, a gradient of a function is itself a vector field. It is itself a vector field. And you might notice here in the little picture, in figure 15, what they've done is they've drawn a contour map. Hold on here, let me try to highlight this. They've drawn a contour map for a particular function. Okay, actually, the function they've drawn the contour map for is x squared y. This is example 6 from section 13.1. X squared y minus y cubed is the function. Okay, and what they're doing is in the picture, so let's keep this in mind, x squared y minus y cubed. So what they do is they draw some level curves of the function of this surface, okay, and they overlap the level curves with gradient vectors, okay, and notice that the gradient vectors are perpendicular to the level curves. And that's absolutely true. That was the principle behind the Lagrange multiplier approach to finding maximum and minimum of functions in section 11.8. Lagrange, subject to a constraint, but Lagrange multipliers, okay? So gradient vectors are perpendicular to level curves. And notice that the gradient vectors are long where the level curves are close to each other and short where the curves fall far further apart. And that makes sense because the length of the gradient vector is a value of a directional derivative, right? The magnitude of the gradient vector is a rate. So the length of gradient vector is the value of the directional derivative of a function, and closely spaced level curves indicate steep graphs. So the function is for instance, as you move along the y-axis, going to -4, the surface is getting steeper. Okay, and that would make sense based on the plot. Okay, let's do a little bit more here, a little bit more. Are there any questions? All right, we're going to finish up section 13.1, and it's really just a kind of section where I give you a guided tour. Now, this is important as well. So, a vector field is called a conservative vector field if the gradient of some function f, is equal to that vector field. So the gradient of a function f equals that vector field. In this situation, the function f is called the potential function. Okay, potential function. How many have heard of a potential function, maybe in a physics class? All right, well, it's fine, no problem. You're learning it here. And not all vector fields are conservative, but such fields do frequently arise in physics. Okay, so for example, they define the function of x, y, z as they have here. And it turns out that the gradient of this function, x, y, z, will equal the vector field for the gravitational field. Okay, so that means that the gravitational field is a conservative vector field because we were able to find a function x, y, and z given by m times little m times big M times g over the square root of x squared plus y squared plus z squared. The gradient of that function is equal to the gravitational field F because the components, I, J, K components, are of the gravitational field. So the gravitational field is a conservative vector field. How many maybe have heard that the gravitational field is a conservative vector field, maybe in a class? Has anybody seen that yet, or is this something that you're going to see? Okay, John's seen it. Robin's seen it. Okay, good, good. So what's really nice here is in chapter 13, you're going to get a calculus treatment of concepts that you have seen or will have seen in some physics and engineering courses. On that note, are there any questions? Okay, let me stop the recording.